A network of deep faults runs right beneath Seattle, and it can shift at any moment, affecting millions of people. The consequences could be as catastrophic as in the past, when a devastating quake lifted the seafloor, collapsed shorelines, and triggered a massive tsunami. It happened in the winter of the year 923. A powerful earthquake hit what is now the Seattle area. It reached around magnitude 7.5, and the impact was terrifying. The ground didn't just shake violently, it shifted. Shorelines collapsed, parts of the seafloor lifted upward, and a tsunami swept through Puget Sound, flooding coastal areas. This event came from the Seattle Fault Zone. This is a complex system of faults that runs directly beneath modern-day Seattle, and it's still active today. This makes it one of the most dangerous geologic threats in the Pacific Northwest. Now, what threat does it present? Well, if a similar earthquake happened now, it would hit a densely populated region, putting millions of people at risk. It would also cause billions of dollars in damage to buildings, roads, and infrastructure. Scientists have started studying this fault more closely to understand how often it produces major earthquakes. They looked at the past 11,000 years to analyze time gaps between large seismic events. Well, the results are kinda mixed. On the one hand, devastating earthquakes, like the one that hit in 923, seem to be extremely rare. In fact, it's the only known quake of that size, magnitude 7.5 or higher, linked to this fault zone. So we can hope that the worst-case scenario, where massive earthquakes like this happen often, is unlikely. But researchers have also made a rather worrying discovery. Smaller earthquakes happen more frequently than expected. And while these quakes may not reach magnitude 7.5, they can still damage buildings, crack roads, disrupt utilities, and trigger landslides. In a modern city like Seattle, even a moderate earthquake can cause really serious problems. In other words, the region still faces regular seismic risk. The fault is active, the pressure builds over time, and the ground can move again. The real danger is the ongoing threat of smaller but still destructive earthquakes, and they may strike with little warning. Now let's take a closer look at the Seattle Fault Zone. It's this huge fault system sitting right under Seattle, a whole network that stretches about 46 miles from the mountains east of the city, all the way to the water on the west side. And yes, it runs directly under Seattle. It's a thrust fault, which means one chunk of ground is slowly pushing up over another. That pressure builds up for a long time, and then suddenly releases. That's when you get a big earthquake. Scientists didn't really start digging into this until the 1990s, when they noticed strange gravity readings. Plus, they found signs that a tsunami had hit the area about 1,000 years ago. All of that pointed to one thing: something catastrophic happened here before, most likely that huge earthquake back in 923. But there was a problem. The data they had managed to gather only went back about 5,000 years. This certainly isn't enough to see a clear pattern. So researchers decided to dig deeper and turn to something called marine terraces. These are old coastlines that got pushed upward by earthquakes and now form something like steps along the shore. Now, an important detail. The 923 earthquake lifted the land by about 26 feet. So scientists started looking for other terraces with the same kind of shift. They mapped out more than 150 of these terraces around Puget Sound, measuring their height and adjusting for natural slopes. It turned out that only one event in an 11,000-year window caused a big uplift like that: the 923 earthquake. As for smaller quakes, those could be hidden under layers of sediment. It means that huge city-shaking earthquakes are very rare, possibly with 5,000 years or even more between them. But it doesn't mean the danger is gone. Smaller ones are what we should worry about. They hit way more often, and they can do serious damage. That's why researchers focused on smaller side faults. Those are called blind faults because you can't see them at the surface, but they can still trigger strong earthquakes. and they already have. One of these smaller faults caused a magnitude 6.7 quake in the past. That's strong enough to damage buildings, crack roads, and mess up infrastructure. So the team pulled together a bunch of tools, like magnetic scans, fieldwork, LiDAR maps. They even dug trenches across fault lines and used dating methods to figure out when past quakes occurred. In the end, they found 3 more earthquakes. One happened around 11,000 years ago. One more hit in the early 1800s. That's a pretty big gap. But it proves these smaller faults have been active for a long time. But the most worrying thing is that these quakes didn't line up with movement on the main fault. That means the smaller faults can rupture on their own. When the team added all this new data together, they saw a pattern. Smaller quakes hit about every 350 years over the last 2,500 years. That's more frequent than scientists used to think. And this activity seems to have picked up over the last 2,000 years. Now, researchers are trying to figure out how big these quakes can actually get, how often they hit, and what would happen if one struck today. But it's not so simple. They have to piece the whole picture together from rocks, layers of soil, and tiny clues they find underground. So, where does it leave Seattle? Well, there's a national system called the Seismic Hazard Model. It's what engineers and planners use to decide how strong buildings need to be, how to design infrastructure, that kind of thing. Right now, this system includes the big 923-style quake, but it doesn't really account for the smaller side faults. First of all, these faults are shorter than what the model usually considers. Second, we're still unsure about how powerful their quakes can get. That's why the model should probably be updated, and authorities need to start planning for those more frequent quakes. It could directly affect building codes and safety plans. Now, despite this worrying news, there are other even more dangerous faults on Earth. Like the San Andreas Fault. It cuts through California for about 800 miles. It's where 2 massive plates slide past each other sideways. That constant grinding builds pressure and then releases it fast. That's how you get quakes like the 1906 San Francisco disaster. Today, millions of people live right on top of it, so scientists track every, even the tiniest tremor with sensors, watching for signs of a bigger break. Then, there's the North Anatolian Fault that runs about 930 miles across Turkey. It tends to break in a chain reaction, one quake triggering the next along the line. In 1999, one of those breaks hit Izmit and took the lives of over 17,000 people. Now the stress is building closer to Istanbul, and that's a city with over 15 million people. The Sumatra subduction zone in Indonesia is where one plate dives under another, locking up tons of energy. In 2004, it unleashed a magnitude 9.1 quake and a tsunami that more than 230,000 people didn't survive. It's still active today, and scientists constantly monitor the seafloor and ocean pressure to catch tsunami signals as early as possible. The Alpi Belt stretches over 1,500 miles from southern Europe to Asia. It once helped build mountain ranges like the Alps. Here, plates crash into each other and push land upward. Quakes don't occur here often, but when they do, they can be powerful and hit heavily populated regions. Japan also sits right where several plates collide. It's one of the most earthquake-prone places on Earth. In 2011, a massive offshore quake triggered a tsunami and the Fukushima disaster. Since then, Japan has built one of the most advanced monitoring systems in the world. Thousands of sensors track ground movement in real time to send out warnings within seconds. Across countries like France, Australia, and the United States, homes are starting to lose their shape. Walls crack and foundations move. Millions of homes are at risk, and yours might be next. The cause isn't earthquakes. The ground itself is shifting. It often starts small, a thin crack on a living room wall. But over time, that line spreads, grows wider, and becomes hard to ignore. Across Australia, more and more homes are starting to show such cracks, all because a long, record-breaking drought is drying out the ground beneath them. And when soil loses moisture, it shrinks. As a result, the foundations of a house can shift unevenly, which puts a lot of stress on the structure. Walls begin to move, and cracks appear. Now, some types of soil make the problem even worse, especially clay. It reacts a lot to water. When it rains, clay soil soaks up the water and swells. When it dries out, it shrinks, kind of like a sponge. The problem is, many areas haven't had much rain for months, and in some places, almost a year. So the soil is drying out way more than it normally would. Recent data shows how extreme the situation has become. Australia experienced one of the hottest and driest years on record. Soil moisture levels have dropped way below average across most of the country. In some parts of New South Wales, especially along the east coast, conditions have worsened quickly. By December, around 48% of the state had soil moisture levels far below average, up from 25% just 1 month earlier. At the same time, plants and trees are trying to survive by pulling even more water from the ground, drying the soil out further and speeding up the process. The result is a vicious cycle. The ground keeps shrinking and foundations keep shifting. Many homeowners, especially around Sydney, spot new cracks or notice old ones grow worse, sometimes in just a few weeks. Moving on to France, more than half of its mainland territory, about 55%, is now classified as being at medium or high risk of house cracking caused by clay soil movement. That's up from 48% in 2020, and it affects more than 12 million homes. Homes built since the 1970s are more at risk because, back then, builders used smaller and shallower foundations. These foundations don't cope well when the ground starts to move. That's why newer rules, introduced in 2024, now require stronger foundations. They have better chances to properly protect homes. A severe drought in 2023, followed by extreme heat, led to a sharp rise in cracks. In some cases, areas can be officially declared natural disaster zones. It allows homeowners to get insurance support for repairs. But it's not that simple. Claims for damage caused by clay soil come with a higher excess, about $1,800, compared with $450 for other types of damage. And proving the damage isn't always easy. One house may crack while the one next door stays fine, which makes it harder to connect the problem directly to weather conditions. Now let's see what's happening in the USA. Carol Devon first thought that her suburban St. Louis home was just settling when small cracks appeared in the walls. But when large gaps opened between her fireplace and the ceiling, and her family room began to tilt, she realized the problem was far more serious. Scott Noche, a 48-year-old physical therapist in Lee's Summit, Missouri, is installing 33 piers, each costing around $1,000 at his two-story home. With added costs for rebuilding the driveway, sidewalks, and landscaping, his total repair bill is expected to reach about $50,000. He first noticed problems last summer when drywall started cracking and doors began sticking. But the situation got even worse during a drought. His back deck sank by about 10 inches, and inside the house, rooms began to tilt, some by up to 4 inches, making movement difficult. Nearly every home on his street has needed similar repairs in recent years. Across the United States, thousands of homeowners are facing the same situation. Movements of soil crack foundations, damage basements, and spread upward into walls and structures. In some areas, gaps wide enough to fit a hand are forming around houses. In many cases, repairs cost tens of thousands of dollars and can even exceed $100,000, often without insurance coverage. In any case, insurance rarely helps. Most policies cover sudden events like fires or floods, not slow ground movement caused by drought. In many cases, claims for this type of damage are denied. Repair companies are struggling to keep up. Cases have been reported in about 40 of the 48 contiguous states, and total damage could go over $1 billion. Cities like St. Louis, where many homes were built with heavy brick structures, experience more damage because brick houses put more weight on foundations than lighter wood or siding homes. This increases strain when the ground moves. Fixing the damage is expensive because it's not just patching cracks. In many cases, contractors must install steel piers under the house to stabilize it. They drive such piers deep into the ground, sometimes down to bedrock, using hydraulic equipment, and the process is very costly. The main thing here is prevention. Homeowners should watch for gaps forming in the soil near foundations, and, if possible, keep the ground evenly moist. Some also use mulch around the house to slow water loss from the soil. The thing is, cracks in walls can look worrying, but in many cases, they don't mean that your house is falling apart. If the soil your house is built on shrinks and swells, depending on the amount of moisture, these cracks might come and go with the seasons. They're likely non-structural, meaning they do not usually affect the safety of the house and its inhabitants. To understand the problem better, you should first check what type of soil your house is built on. You can ask local councils or request geotechnical reports from building permits. They might give you this information. There are ways to reduce the movement of your house, but most are easier to apply during construction. For example, stronger foundations can help, but they're expensive and not always practical for already existing homes. Once cracking has started, it is difficult to fully stop it. You can only control how much moisture the soil around the house gets. Some people try removing trees near the house, since roots can draw water from the soil. But this can actually backfire. Cutting trees can suddenly change moisture levels in the ground and make the soil even more unstable. Another way is to build a barrier around the house, like a concrete strip or paved area. This pushes the wet and dry zones away from the walls and helps reduce soil movement right under the house. Watering lawns is also tricky. Too little water dries the soil too much, but too much water can create uneven moisture around the house and cause more movement instead of less. So, as you see, there is no simple fix. Experts recommend getting a professional assessment before taking action. An independent structural engineer or building consultant can help identify whether cracks are harmless or part of a bigger problem. Over the past century, human activity has trapped more heat in the Earth's atmosphere. This extra heat is changing the planet's climate, and scientists say Earth is now holding more energy than it releases. Because of this, the weather is becoming more extreme, with terrible storms and droughts. In some places, strong snowstorms block roads and disrupt transport. In the United States, tornado seasons are becoming more intense than expected. In other regions, heavy rain causes flash floods and serious damage. The year 2025 was one of the hottest years ever recorded. Most of this extra heat doesn't stay in the air. It goes into the oceans instead. About 91% of it is absorbed by the sea, which is warming ocean water and disturbing marine life. Scientists warn that if this continues, ocean systems could reach dangerous tipping points.
We are on the Sea of Marmara, the exact spot where the massive continents of Europe and Asia meet. It's a vital, beautiful waterway packed with cargo ships on the surface, but dive underneath and you'll find a geographical nightmare lying on the seafloor. Deep underwater, two massive slabs of the Earth's crust are violently grinding past each other. This isn't just a minor crack in the dirt, it's a colossal geological fault. A massive complex system of continuous fractures that has been accumulating a devastating amount of energy for decades. We call it the Great North Anatolian Fault. All this energy has to be unleashed someday. And when it happens, it's going to hit one of the most densely populated areas on our planet. Scientists are now in active monitoring mode, especially when it comes to Turkey. This country is sitting on the Anatolian Plate, a small bite of the Earth's crust, Nowadays, it's being literally smashed by the Arabian Plate from the south and the Eurasian Plate from the north. Because it's being squeezed so hard, the only direction it can move is west toward the Aegean Sea, and it actually does this at a speed of about 1 inch per year. In geological terms, that's a high-speed, violent movement. Millions of tons of solid rock grinding against each other deep underground day and night without a single break? Not the best thing to experience. All this endless moving, cracking, and squeezing is what creates the North Anatolian Fault, a 930-mile-long fault line that acts almost exactly like the infamous San Andreas Fault. Yet the difference is striking. While the San Andreas mostly skirts the outer edges of Californian megacities or runs through less dense regions, the fault in Turkey is running right under major industrial hubs and heavily populated urban centers. In February 2023, the smaller sister of it, the East Anatolian Fault, showed us how dangerous this tectonic setup can be. It generated the most catastrophic earthquake recorded in Turkey in over 60 years, a brutal 7.8 monster hit and a 7.5 shockwave followed right behind it just hours later. The release of energy was so violent that the ground literally moved by almost 10 feet in some places. Entire cities were leveled and the physical map of the region permanently shifted. Now the worst part, it wasn't even the grand finale. There's no way to stop that energy packed inside the North Anatolian Faults. Look at the old data and you'll see it acts like clockwork, a bit like a line of falling dominoes. Scientists have been tracking every sequence of earthquakes in this region for nearly a century. The whole chain reaction started in 1939 with the catastrophic Erzincan earthquake. A massive magnitude 7.8 struck eastern Turkey. It didn't simply release the energy, but also transferred this tectonic stress into the next section of the fault. Dominoes started falling. Other fault ruptured happened in 1942, 1943, and 1944. It went west and struck again in 1957 and 1967. Year by year, the epicenters of these massive earthquakes moved in a straight line toward the Sea of Marmara. The last major impact was the Izmit earthquake in 1999. A magnitude 7.6 tremor struck east of Istanbul and lasted for 37 terrifying seconds. Suddenly, the chain reaction took a break, but the tectonic stress was still there, simply transferred to the next section of the fault, under the Sea of Marmara, where the last major earthquake took place in 1766. Nobody had seismographs back then, but historical records and old journals describe it as a scene of unimaginable horror. Now, modern science tells us exactly why it was so devastating. Scientists are calling it a seismic gap, basically a dangerously quiet zone that hasn't ruptured yet. Back then, 260 years ago, a massive quake destroyed a huge part of Istanbul and generated a tsunami that crashed into the city's ports. After this tragedy, it didn't happen again on this scale, but we have to remember that the Anatolian Plate has never stopped moving west, an inch a year. Let's do some quick math. That land should have moved by over 19 feet by now, but because those rocks are locked together, they haven't moved an inch. We are looking at a massive backlog of tectonic tension. It simply has to snap finally, and it won't make a regular shake. It will likely rapidly release 2.5 centuries of accumulated tectonic energy, right at the doorstep of Europe and Asia. The target is the city of Istanbul once again. We should call it a supercity because this global mega hub is home to an astonishing 15 million people. It accounts for nearly 30% of Turkey's entire economic output. What about the infrastructure? We're talking about 1 million buildings, and an estimated 90,000 of those are at high risk of total collapse in the event of a magnitude 7.5 earthquake. Nowadays, the city has very strict laws for modern buildings. But plenty of urban areas had been built before those regulations were enforced. To make matters worse, many coastal neighborhoods are built on soft, waterlogged soil that acts like a liquid during extreme shaking, multiplying the danger for the residents. Buildings could just sink into quicksand. And there's more. The seafloor of the Marmara Sea isn't flat. There are 3 massive deep underwater holes separated by vast ridges. Why is it important? A stronger earthquake in this area will probably trigger a massive submarine landslide. Plenty of mud and rock collapsing down those underwater canyons would instantly displace massive amounts of water. This would trigger a tsunami, not as tall as mega tsunamis in the open Pacific Ocean, but still highly dangerous. It's estimated that with a 10-foot wall of water, it will be extremely dangerous for this densely populated area. Scientists also claim that it could hit the coastline within 10 minutes. There would be almost no time for a mass evacuation. Here comes modern technology. Engineers are fully aware that this geographical clock is ticking and are fighting back. Essentially, infrastructure is being heavily retrofitted. Also, the mighty bridges crossing the Bosphorus Strait have been reinforced with seismic dampers to absorb extreme shocks. One of the world's largest seismically isolated buildings is located at Sabiha Gökçen International Airport in Istanbul. It's sitting on massive bearings made out of rubber and steel. The absolute art of engineering is the Marmara Tunnel, a massive railway tube that runs directly under the Bosphorus Strait, physically connecting the European and Asian continents underwater. It was built right next to an active fault line, so it had to be designed with flexible earthquake-proof joints. If a megaquake hits and the continents shift, the tunnel will bend and flex like a giant snake rather than snapping in half. Another concern of scientists is the economic aftershock of this rupture. It may affect the entire globe, as the Bosphorus Strait is one of the world's most critical maritime choke points. Every single year, nearly 50,000 ships pass through this narrow waterway, carrying everything that is crucial for the global market: barrels of oil, agricultural goods, and so on. The price of energy and food would go crazy if this shipping line collapses. To buy some precious time, scientists have installed an advanced early warning network on the seafloor of the Marmara Sea. Fiber optic cables and seismometers are constantly listening to the fault. But because the epicenter is located so incredibly close to the city, even this multi-million-dollar system won't give residents enough time to escape. At best, it will provide a maximum of 5 to 7 seconds of warning before the destructive waves hit the city. 5 seconds to shut down gas lines, halt the trains, and brace for the impact. Of course, all this effort won't protect the whole city. Only a fraction will survive. The undeniable conclusion is that the migration of earthquakes isn't just a theory, but a well-documented geographical reality. Scientists estimate that there is a 65% probability of a magnitude 7 or greater earthquake striking the Sea of Marmara region before the year 2030. Now we can see that the rupture in this area isn't just a possibility. It is coming, and it is migrating directly toward the collision point of 2 continents. Australia feels like the safest place on Earth, geologically speaking. No megavolcanoes, no massive fault lines slicing cities in half, no constant earthquake alerts. It looks solid and unbreakable, but according to a brand new global stress map of Earth's crust, Australia is one of the most internally stressed pieces of land on the entire planet. It's not shaking or cracking yet, but it's quietly storing energy like a bent ruler about to snap. To understand why this is such a big deal, imagine Earth's crust like a giant jigsaw puzzle made of moving slabs called tectonic plates. These plates float on softer rock below and push, pull, or grind against each other. Where plates meet, earthquakes and volcanoes make sense. But stress doesn't just stay at the edges, it travels. It builds up inside plates too, like pressure spreading through frozen ice when you squeeze it. Scientists mapped over 100,000 real stress measurements from oil wells, rock tests, and earthquakes to see where Earth is being squeezed the hardest right now. When they laid all the data together, the map lit up like a warning sign, and Australia stood out. This shocked scientists because Australia sits far away from plate boundaries, which usually means stability. But instead of relaxing, the Australian continent gets squeezed from multiple directions by nearby plates, especially the Pacific and Eurasian ones. The stress doesn't release easily, so it piles up inside the crust, and then nothing moves. Until suddenly everything does. One of the strangest discoveries showed up in places like the Bowen Basin, where stress directions twist and rotate underground. That's bad news because unpredictable stress behaves like glass about to shatter. These rotating stress fields make it nearly impossible to say when or where cracks could form. It could be years away or tomorrow. And human activity makes it even riskier. Drilling deep into the crust for geothermal energy or injecting fluids underground can nudge these stressed zones just enough to trigger fault movement. This doesn't mean Australia is about to split in half next week, but it does mean the idea of geologically safe might be outdated. Scientists now think Australia could eventually fracture internally and form new fault systems where none existed before. What makes the new stress map different from older models is that it doesn't just explain past earthquakes, it helps identify future risk zones before anything breaks. Countries can use this data to decide where drilling is safer, where tunnels shouldn't go, and where infrastructure needs reinforcement. But even with all this data, we still can't predict the exact moment Earth will snap. Stress maps tell us where the tension is. They don't tell us when it gives up. But this idea of continents quietly tearing themselves apart isn't just theory. Africa gives us the clearest real-world example. It's slowly unzipping itself. So slowly that no human will ever wake up and see a new ocean where land used to be, but fast enough that scientists can actually measure it happening right now. Deep beneath East Africa, the ground stretches, thins, and pulls apart as if the continent is taking a deep breath and never fully exhaling. And over millions of years, that stretch could turn into an ocean. This whole process centers on something called the East African Rift System, or EARS for short. Think of it like a giant tear running through the continent, thousands of miles long, cutting through countries like Ethiopia, Kenya, Tanzania, and Mozambique. It's one of the biggest rift zones on Earth. A rift zone is exactly what it sounds like, a place where the planet's crust is being pulled apart instead of squeezed together. And Africa just happens to have one of the most dramatic examples anywhere on the planet. What's really happening is that Africa isn't one solid plate anymore. It's splitting into two massive chunks, the Nubian plate to the west and the Somalian plate to the east. These two plates are drifting away from each other at a speed that sounds laughable, just less than an inch per year. That's about the speed your fingernails grow. But give that process millions of years and suddenly continents don't look so permanent anymore. In 2018, photos of a giant split in Kenya went viral across the internet. Headlines screamed that Africa was splitting in half right now. It looked dramatic, but that moment didn't mean Africa suddenly broke overnight. That rupture was more like a surface ripple, a small local sign of a much bigger process that's been going on for around 25 million years. And if we could travel in time to 5 or 10 million years from now, we would probably see the crust thin enough for seawater to rush in. When or if that happens, East Africa would slowly peel away from the rest of the continent, and a brand new ocean basin would form between the two plates. Africa would lose its eastern shoulder, and maps of the world would need a serious update. As strange as that sounds, it's actually totally normal for Earth. The planet never stops reshaping itself. It just works on a timeline so slow that our brains struggle to process it. The continents we know today feel ancient and permanent, but they're basically temporary arrangements. About 138 million years ago, South America and Africa were locked together like puzzle pieces. You can still see it if you look at their coastlines. They match almost perfectly. East Africa drifting away will just be the next chapter in that story. Australia's story could follow a different path, but the physics are similar. Stress builds, rock resists, then the rock fails. And stress doesn't care about borders, cities, or how calm the surface looks. That's why scientists are so concerned about something called SH max, the direction of maximum horizontal stress. In simple terms, it tells us which way the Earth is squeezing the hardest underground. If that squeezing lines up with existing fractures, earthquakes become more likely. If it cuts across old faults, new ones can form. Turkey is another place where the stress map practically screams danger. The country sits where Arabian, Eurasian, and African tectonic plates collide. There's also a smaller Anatolian plate on which Turkey is located, and which gets squeezed westward like toothpaste, grinding against massive faults. The stress map shows SH max pointing in directions that load these faults perfectly. Now, researchers looked at ancient lava flows near one of Turkey's faults and realized they weren't random. Lava sheets once flowed smoothly across the land, cooled into solid rock, and then got pulled apart over time, like a snapped chocolate bar. That gave scientists a rare, clear snapshot of how continents deform from the inside out. To date the lava, the team used microscopic zircon crystals trapped inside it. These crystals work like natural stopwatches. They trap helium created by radioactive decay, and by measuring that helium, scientists can tell when the lava erupted and cooled. When they combine that with satellite images and remote sensing, the scientists managed to see Earth's slow-motion movements. The Tuzgolu Fault stretches more than 120 miles and is so massive that you can spot it from space. For years, scientists assumed it behaved like many of Turkey's dangerous faults, where land slides sideways past itself. But this new research flipped that idea on its head. The fault isn't sliding, it's slowly ripping open. The land on either side moves away from each other at less than an inch per year. That sounds tiny, but then again, over thousands or millions of years, that motion adds up to continents literally thinning and breaking. And since the fault sits where three massive tectonic plates meet, this matters way beyond Turkey. All this once again reminds us that continents don't just collide or slide. Sometimes they stretch until they snap. And places that look calm on the surface might already be under invisible strain, inch by inch, year after year, rewriting the map long before anyone feels the shake. Turkey may need to brace itself for one of the most devastating megaquakes we've ever seen. New 3D models suggest a major fault line just outside Istanbul has been building pressure for centuries, and it could rupture at any time. What's crazy is that the sun could help set it off. Up in space, powerful solar bursts can mess with Earth's magnetic field. That can trigger geomagnetic storms which send electric currents through the ground. And if a fault is already under extreme stress, like this one in Turkey, some researchers argue that extra electromagnetic energy could be the final push. This mega earthquake will probably start right here, in the Sea of Marmara. It separates Turkey's Asian side from its European side. And at first glance, it doesn't look dangerous at all. No strong currents, no scary sharks, and it's even considered the smallest sea in the world. But the real danger is actually underneath it. The Sea of Marmara is deep. Its deepest point is about 4,500 feet, and way down there runs the North Anatolian Fault, or just the NAF. This is a long, active right lateral strike-slip fault that stretches across northern Turkey. In simple terms, it's the boundary where the Eurasian plate and the smaller Anatolian plate slide past each other. It's very similar to California's San Andreas Fault in size, slip rate, and overall behavior. And just like in the US, this fault in Turkey can also trigger powerful earthquakes. One of the most catastrophic ones is known as the Erzincan earthquake. On December 26, 1939, a long section of the North Anatolian Fault suddenly ruptured. The ground on both sides of the fault snapped past each other, unleashing a massive quake that hit the Erzincan region. It was devastating, Around 116,000 buildings were destroyed, more than 100,000 people were affected, and over 30,000 lost their lives. Ever since that tragedy, researchers have been keeping a close eye on the fault, and they've noticed a pretty scary pattern. Big, destructive earthquakes along this fault don't happen randomly. They seem to march westward over time. And that's why one particular stretch under the Sea of Marmara is getting so much attention, especially because it's, well, quiet. Okay, maybe not that quiet. This area has had earthquakes in recent years, and they've been getting stronger. Since 2011, the quakes have gradually increased in magnitude, leading up to the magnitude 6.2 Marmara earthquake in 2025. That was the biggest event on this fault in more than 60 years. But when I say quiet, I mean that it hasn't had a truly major quake since 1766, something above magnitude 7 on the Richter scale. To put that into perspective, that's about the same power as the 2010 Haiti earthquake, where about 160,000 people lost their lives. Not having a big quake in centuries in Turkey sounds like good news, but it's actually very concerning. When you don't see big movement for a long time, it can mean stress is piling up beneath the fault, and that makes it a high-risk zone. Earlier studies from 2023 found that the fault beneath the Sea of Marmara is split into several different sections, and they don't all behave the same way. In the west, for example, the fault moves very slowly. That can cause smaller recurring earthquakes. So instead of one huge event, some of the energy gets released little by little. But as you move east, that slow movement happens less often. And just south of Istanbul, the fault doesn't seem to move at all. It's basically locked. All these areas are under stress because tectonic plates keep pushing from underneath. And on top of that, past earthquakes can also add even more stress to the system. But the biggest concern is that locked section. It doesn't release enough energy through small shakes, so the pressure can keep building. And since the nearby sections are still creeping along, they can add even more strain and concentrate stress in one spot. And when that built-up energy finally releases, trust me, you don't want to be anywhere near it. All that pressure could trigger a major devastating earthquake, possibly one of the biggest in Turkey's modern history. But there's a problem. It's incredibly hard to study this region. That's because this part of the North Anatolian Fault is basically invisible to us. It's underwater. It's been relatively quiet for centuries, and its detailed 3D structure isn't easy to detect using traditional mapping methods. So how do you even study something like that? Without a clear image, it's almost impossible to know how dangerous this zone really is. Thankfully, researchers may have found a solution. Scientists from the Institute of Science Tokyo used electromagnetic imaging to map it, almost like taking an X-ray of the Earth. They used something called magnetotellurics. Basically, it lets scientists detect tiny changes in Earth's electric and magnetic fields, changes caused by structures deep underground. Using that, they built the first 3D map of the North Anatolian Fault based on something called resistivity, which is how strongly rocks resist electric current. This map helped them spot locked zones, where stress has been building up for a long time. And the boundaries around those locked areas could be exactly where the next major rupture starts, giving Turkey a much clearer idea of where the biggest risk may be and how to prepare. And they really need that, because the area where this could happen is dangerously close to Istanbul. This is Turkey's biggest city with around 15 million people, and it's also the country's main industrial hub. It's a real economic powerhouse, generating close to 40% of Turkey's GDP every year. So yeah, a major quake near Istanbul wouldn't just shake the city, it could shake the whole country, economically speaking. That brings us to the big question: when could it happen? That's still a mystery, but it might be sooner than people think. Historical records going back more than 2,000 years suggest that big earthquakes in this particular region tend to repeat about every 250 years on average. And since the last major one was in 1766, that's not great news for Turkey. Do the math and you'll see why people are worried. The main Marmara Fault is already late in its seismic cycle, which means it has the potential to produce a large earthquake at any time. But it's not like Turkey is caught off guard. The country knows these risks, and it's been staying on top of them. For years, they've been working on ways to reduce the damage when the next big quake hits. Because in a situation like this, being fast doesn't just help, it can save lives. That's why they've been upgrading their earthquake early warning system. The goal is to catch the very first signals of a quake, the P waves. They're the first waves to hit, and they're weaker. The S waves are the ones that do more damage. Normally, it takes about 5 or 6 seconds to catch these P waves and send an alert, but this newer technology can do it in just 0.2 seconds. That's incredibly fast. The problem is, there still aren't enough sensors on the ocean floor, so the signal hits the coast about 6 seconds late, which limits how early the warning can come, at least for now. Still, the progress is real. In October 2025, the upgraded system made its debut and sent its first alert in just 8.4 seconds after a magnitude 5 quake struck the Sea of Marmara. And that's a big deal, because every second can trigger automatic safety actions, slowing trains, stopping elevators, shutting down gas lines, and giving people just enough time to react. The next step is to place more sensors on the seabed, so they can buy even more time. And if Turkey keeps preparing and investing in this kind of technology, the next major earthquake may be a lot less dangerous than we think. We are on the Sea of Marmara, the exact spot where the massive continents of Europe and Asia meet. It's a vital, beautiful waterway packed with cargo ships on the surface, but dive underneath and you'll find a geographical nightmare lying on the seafloor. Deep underwater, 2 massive slabs of the Earth's crust are violently grinding past each other. This isn't just a minor crack in the dirt, it's a colossal geological fault. A massive complex system of continuous fractures that has been accumulating a devastating amount of energy for decades. We call it the Great North Anatolian Fault. All this energy has to be unleashed someday. And when it happens, it's going to hit one of the most densely populated areas on our planet. Scientists are now in active monitoring mode, especially when it comes to Turkey. This country is sitting on the Anatolian Plate, a small bite of the Earth's crust. Nowadays, it's being literally smashed by the Arabian Plate from the south and the Eurasian Plate from the north. Because it's being squeezed so hard, the only direction it can move is west toward the Aegean Sea, and it actually does this at a speed of about 1 inch per year. In geological terms, that's a high-speed, violent movement. Millions of tons of solid rock grinding against each other deep underground day and night without a single break? Not the best thing to experience. All this endless moving, cracking, and squeezing is what creates the North Anatolian Fault, a 930-mile-long fault line that acts almost exactly like the infamous San Andreas Fault. Yet the difference is striking. While the San Andreas mostly skirts the outer edges of Californian megacities or runs through less dense regions, the fault in Turkey is running right under major industrial hubs and heavily populated urban centers. In February 2023, the smaller sister of it, the East Anatolian Fault, showed us how dangerous this tectonic setup can be. It generated the most catastrophic earthquake recorded in Turkey in over 60 years. A brutal 7.8 monster hit and a 7.5 shockwave followed right behind it just hours later. The release of energy was so violent that the ground literally moved by almost 10 feet in some places. Entire cities were leveled and the physical map of the region permanently shifted. Now the worst part, it wasn't even the grand finale. There's no way to stop that energy packed inside the North Anatolian Faults. Look at the old data and you'll see it acts like clockwork, a bit like a line of falling dominoes. Scientists have been tracking every sequence of earthquakes in this region for nearly a century. The whole chain reaction started in 1939 with the catastrophic Erzincan earthquake. a massive magnitude 7.8 struck eastern Turkey. It didn't simply release the energy, but also transferred this tectonic stress into the next section of the fault. Dominoes started falling. Other fault rupture happened in 1942, 1943, and 1944. It went west and struck again in 1957 and 1967. Year by year, the epicenters of these massive earthquakes moved in a straight line toward the Sea of Marmara. The last major impact was the Seismic earthquake in 1999. A magnitude 7.6 tremor struck east of Istanbul and lasted for 37 terrifying seconds. Suddenly, the chain reaction took a break, but the tectonic stress was still there, simply transferred to the next section of the fault, under the Sea of Marmara, where the last major earthquake took place in 1766. Nobody had seismographs back then, but historical records and old journals describe it as a scene of unimaginable horror. Now, modern science tells us exactly why it was so devastating. Scientists are calling it a seismic gap, basically a dangerously quiet zone that hasn't ruptured yet. Back then, 260 years ago, a massive quake destroyed a huge part of Istanbul and generated a tsunami that crashed into the city's ports. After this tragedy, it didn't happen again on this scale. But we have to remember that the Anatolian plate has never stopped moving west, an inch a year. Let's do some quick math. That land should have moved by over 19 feet by now. But because those rocks are locked together, they haven't moved an inch. We are looking at a massive backlog of tectonic tension. It simply has to snap finally, and it won't make a regular shake. It will likely rapidly release 2.5 centuries of accumulated tectonic energy, right at the doorstep of Europe and Asia. The target is the city of Istanbul once again. We should call it a supercity because this global mega-hub is home to an astonishing 15 million people. It accounts for nearly 30% of Turkey's entire economic output. What about the infrastructure? We're talking about 1 million buildings, and an estimated 90,000 of those are at high risk of total collapse in the event of a magnitude 7.5 earthquake. Nowadays, the city has very strict laws for modern buildings. But plenty of urban areas had been built before those regulations were enforced. To make matters worse, many coastal neighborhoods are built on soft, waterlogged soil that acts like a liquid during extreme shaking, multiplying the danger for the residents. Buildings could just sink into quicksand. And there's more. The seafloor of the Marmara Sea isn't flat. There are 3 massive deep underwater holes separated by vast ridges. Why is it important? A stronger earthquake in this area will probably trigger a massive submarine landslide. Plenty of mud and rock collapsing down those underwater canyons would instantly displace massive amounts of water. This would trigger a tsunami, not as tall as mega tsunamis in the open Pacific Ocean, but still highly dangerous. It's estimated that with a 10-foot wall of water, it will be extremely dangerous for this densely populated area. Scientists also claim that it could hit the coastline within 10 minutes. There would be almost no time for a mass evacuation. Here comes modern technology. Engineers are fully aware that this geographical clock is ticking and are fighting back. Essentially, infrastructure is being heavily retrofitted. Also, the mighty bridges crossing the Bosphorus Strait have been reinforced with seismic dampers to absorb extreme shocks. One of the world's largest seismically isolated buildings is located at Sabiha Gökçen International Airport in Istanbul. It's sitting on massive bearings made out of rubber and steel. The absolute art of engineering is the Marmara Tunnel, a massive railway tube that runs directly under the Bosphorus Strait, physically connecting the European and Asian continents underwater. It was built right next to an active fault line, so it had to be designed with flexible earthquake-proof joints. If a megaquake hits and the continents shift, the tunnel will bend and flex like a giant snake rather than snapping in half. Another concern of scientists is the economic aftershock of this rupture. It may affect the entire globe, as the Bosphorus Strait is one of the world's most critical maritime choke points. Every single year, nearly 50,000 ships pass through this narrow waterway, carrying everything that is crucial for the global market: barrels of oil, agricultural goods, and so on. The price of energy and food would go crazy if this shipping line collapses. To buy some precious time, scientists have installed an advanced early warning network on the seafloor of the Marmara Sea. Fiber optic cables and seismometers are constantly listening to the fault. But because the epicenter is located so incredibly close to the city, even this multi-million-dollar system won't give residents enough time to escape. At best, it will provide a maximum of 5 to 7 seconds of warning before the destructive waves hit the city. 5 seconds to shut down gas lines, halt the trains, and brace for the impact. Of course, all this effort won't protect the whole city. Only a fraction will survive. The undeniable conclusion is that the migration of earthquakes isn't just a theory, but a well-documented geographical reality. Scientists estimate that there is a 65% probability of a magnitude 7 or greater earthquake striking the Sea of Marmara region before the year 2030. Now we can see that the rupture in this area isn't just a possibility. It is coming, and it is migrating directly toward the collision point of two continents. Scientists just found out that the Earth's crust beneath the Marmara Sea is sending seismic signals that look exactly like the kind that show up before a major earthquake. An earthquake that can shake entire coastlines and send waves racing toward crowded cities. For years, scientists focused on visible ruptures on land because they could measure and map them easily. But now, they made a detailed map of a huge fault system under the seafloor. The Mediterranean already sits at a dangerous crossroads where massive tectonic plates meet. Those plates push, scrape, and stretch against each other, and that constant motion creates massive stress. The crust there grows thinner over time, and thinner crust means it can't absorb stress easily. Stress builds, pressure mounts, and the signals coming from below show that parts of this fault system have started to move in unusual ways. The new map shows that future large earthquakes may begin at the boundaries where weaker and stronger sections of the crust meet, or along edges of highly resistive zones. They even pinpointed one of the most likely locations, beneath the Marmara Sea. What makes this discovery so intense is the scale. The faults in the seabed form long corridors where energy can accumulate for decades or centuries. Scientists warn that this setup is the kind that can produce a super earthquake, a massive seismic event capable of shaking large coastal cities and possibly generating tsunamis. A tsunami forms when the seafloor shifts vertically and displaces huge amounts of water, so it looks really plausible in this setting. The water it sets free radiates outward in powerful waves that can cross entire seas. The Mediterranean holds dozens of densely populated shorelines, so it could affect millions of lives. Speaking of that, let's zoom in on Istanbul, Turkey's largest and most populous city. The massive fault line sitting right under it doesn't act the way scientists thought it did. For years, experts looked at the main Marmara Fault, a branch of the North Anatolian Fault running beneath the Sea of Marmara, and worried it might rip in one single monstrous rupture. That kind of break could unleash a megaquake in the high 7s or beyond. But when scientists ran detailed computer simulations covering more than 10,000 years of earthquake cycles, they saw something different. The fault doesn't behave like one giant zipper waiting to unzip all at once. It behaves more like a row of connected tiles that break in sections. And the reason comes down to what's happening miles below the seafloor. It's called rheology. Simply put, how materials deform under stress, how rocks bend, stretch, or snap when you squeeze them hard enough. Under the central Sea of Marmara, giant piles of compacted mud, sand, and debris sit on top of warmer crust. In those upper layers, the sediment usually deforms slowly and steadily, especially at shallow depths where pressure and heat interact in specific ways. Deeper down, higher temperatures weaken the rocks. Warm rock flows more easily than cold rock. That heat acts like a built-in brake system that limits how far a rupture can tear through the crust. When researchers built a 3D earthquake cycle model, they fed in real heat flow measurements, rock friction data, and structural details, and replayed thousands of years of seismic activity. When they included both sediment thickness and temperature differences, the model finally matched history, including the powerful quakes of 1766 and 1912. And none of the simulated events exceeded magnitude 7.3. That level of shaking can collapse buildings, fracture infrastructure, and cause landslides. But it differs from the nightmare scenario of one continuous coast-to-coast rupture. Instead, different sections behave in different ways. The western segments produce more regular earthquakes, including magnitude 7.2 events roughly every 150 years. The eastern sections generate smaller double quakes, back-to-back events between magnitude 6.2 and 6.8 about every century, and a magnitude 7.0 roughly every 500 years. Parts of the fault don't snap at all, but creep. Scientists call it shallow creep, which just means the fault slowly slides without producing a major quake. It releases tension quietly, like letting air out of a balloon instead of popping it. GPS measurements and clusters of repeating small quakes over the past 20 years confirm that slow slip near the central basin. So what does this mean for Istanbul, a city of over 15 million people sitting practically on top of this system? A magnitude 7 or 7.3 quake close to the city could still rock neighborhoods, especially if two strong events strike in quick succession. Infrastructure, older buildings, and densely packed districts are at the highest risk. The fault hasn't produced a major rupture in this section since 1894, which means there's more than 130 years of accumulated strain. The simulations show major events could strike in the coming decades. Then there's Santorini, where more than 28,000 earthquakes happened in just a few months in early 2025. Most of the quakes stayed small, but some reached magnitude 5, strong enough to fracture walls, rattle nerves, and push authorities to close schools and evacuate parts of the island. And this wasn't just tectonic plates grinding like they usually do. This swarm moved. The epicenters shifted gradually northeast toward the Colombo submarine volcano about 5 miles offshore. That migration told scientists magma was on the move. Researchers calculated that roughly 80 billion gallons of it, enough to fill about 120,000 Olympic swimming pools, surged upward from depths around 11 miles beneath the surface. It climbed fast, then stalled about 2 to 2.5 miles below the seafloor. And all this was going on along the Hellenic Arc, one of Europe's most active subduction zones, where the African plate dives beneath the Eurasian region. Earthquakes often migrate across that span toward nearby islands. History backs that up. The 1956 Amorgos earthquakes unleashed massive shaking and a tsunami across the region. So, when 28,000 tremors light up the seismic network, you pay attention. This episode changed how scientists understand volcanic swarms. Now they know magma can intrude, fracture miles of crust, reshape underground reservoirs, and still never surface. It can load the system for the future without pulling the trigger today. And that matters because when magma moves like this, it changes stress fields underground and how future quakes might breed. The good news is that scientists now have really cool monitoring tools that feed real-time seismic feeds, underwater pressure sensors, and repeated gas measurements near volcanic vents into integrated hazard models. If magma starts accelerating upward again, researchers will see it and will take action. And there's another bold new idea in earthquake and tsunami warning: using undersea internet cables for this purpose. Nearly 1 million miles of those fiber optic lines on the seabed were designed to carry data, but scientists discovered that they can also detect tiny changes in light signals caused by seismic vibrations. In simple terms, when the ground shakes, the cable feels it. And this could be incredibly useful because forecasting earthquakes, even on land, is tricky. In the ocean, it has felt almost impossible as you can't scatter thousands of sensors across the seafloor easily. But those cables already sit there, stretching across deep trenches and continental shelves. If researchers use them as sensors, they can monitor tectonic movement in real time across huge areas. For a region like the Mediterranean, with hidden faults, active volcanoes, and crowded coasts, that system could offer precious seconds or minutes of warning. Seconds sound small, but early alerts let trains stop, gas lines shut down, and people move away from immediate danger. The fiber optic cable used for Seafloor Project, or FOCUS in the short version, didn't warn anyone about real disasters yet, but it had two false alarms. It reacted to a submarine landslide and weight bags that pushed the cables down. It proves the system works and could be life-saving in case of real danger, especially in vulnerable regions such as the Mediterranean. It shaped civilizations for thousands of years, and now science reveals it still shapes itself. They can't stop tectonic plates or cool magma chambers, but they can understand patterns, reduce vulnerability, and design cities smarter. Something is about to reshape the entire future of the West Coast. The coastline, the infrastructure, the whole map. Scientists fear there is not one but two big earthquakes coming, one caused by another. This wasn't even on the radar for most people, but new research is changing everything. For decades, everyone treated the San Andreas Fault and the Cascadia Subduction Zone like two separate monsters that just happened to live in the same neighborhood. They were powerful, yes, but independent. But now, scientists believe these two giant faults are mechanically linked, and one can literally pull the other into rupturing shortly afterward. Cascadia moves, San Andreas moves. San Andreas tears, Cascadia tears. And the potential consequences of that are honestly haunting. Scientists found evidence that it happened at least 10 times in the last 3,100 years. Earthquake, pause, earthquake. It comes from marine sediment cores, which are like time capsules pulled up from the ocean floor. Researchers analyzed layer after layer of seabed sediment and found doublets, paired debris layers created by two massive quakes happening so close together that the ocean barely had time to settle between them. That discovery takes us to the Mendocino Triple Junction, the geological troublemaker of the West Coast. It's the place where three tectonic plates crash and grind into each other like badly aligned gears. It's also the zone where the San Andreas meets Cascadia, which makes it the perfect place for these double quakes to form. The stress changes caused by a rupture in one fault travel straight through this junction and destabilize the other. It's benign when it happens to a bookshelf. When you move one book, three others shift. But when you think about it like a coastline with millions of people, entire cities, major infrastructure, it instantly feels terrifying. To many people who live on the West Coast, the San Andreas kind of feels like a California's problem, and Cascadia like an Oregon and Washington's problem. But when you understand that these two faults can essentially fire at each other, it stops being a local issue and becomes a continental one. A Cascadia megaquake alone can hit magnitude 9.0 plus, rip open 600 to 700 miles of seafloor, and send a tsunami roaring toward the Pacific coast. And it could just be the first quake, and then, maybe minutes later, the San Andreas snaps in Northern California. The shaking could ripple down the state like a zipper tearing open a jacket, and if it goes the other direction, it could be just as bad. If the San Andreas ruptures first, the intense stress redistribution can destabilize the Cascadia subduction zone. You could get the California quake first with buildings rocking, highways breaking, and power stations failing. And then, soon after, the ocean pulls back in Oregon or Washington. And the 20-minute countdown to a tsunami begins, a follow-up disaster. It's the kind of chain reaction you don't want even in a video game, let alone real life. This discovery also tells us something eerie about the earthquake in 1700, the one that sent a tsunami across the Pacific so huge that it struck Japan with no warning. Japanese fishermen called that wave the orphan tsunami, because it arrived without any felt shaking. Only centuries later, scientists figured out that it came from the Pacific Northwest. But until recently, no one knew that the San Andreas might have felt that event too, and it possibly slipped or destabilized because of it. So, the whole West Coast may have moved together. And we've come to the scariest part. All this isn't about if, it's strictly about when. The faults have a rhythm, a pace, and a geological heartbeat. We've seen how they behave across thousands of years. We know what they did, and now we know they sometimes do it in sequence. The real fear isn't the first quake. California already expects a big one. The real fear is the second quake, the one that comes before you've checked on your family, before emergency responders regroup, before the power comes back, and before the dust settles. Even if you don't live on the West Coast, this matters for you too. The ports in California, Oregon, and Washington handle a massive chunk of America's imports. Knock them offline, and it's not just the coastline that feels it. The ripple hits the entire country and potentially the world. Grocery prices spike, supply chains freeze, gas availability dips, shipping timelines go nuts. The world is much more connected than any of us thought, and a geological double punch on the Pacific coast wouldn't stay a local disaster. It would spread, thread by thread, into everyone's life. So, those in power must prepare not for one giant rupture, but for two. Emergency plans, evacuation routes, response times, and power grid designs, all of it needs updating. Because nature has now shown us what even a single major rupture can do to a modern economy. It happened in Japan in 1995, on January 17th at 5:46 in the morning. The quake hit right by the northern tip of Awaji Island, only 12 miles from Kobe, a huge, busy city with about 1.4 million people back then, and another 2.6 million in Osaka nearby. The rupture ripped along the Nojima Fault for about 25 miles. That doesn't sound like much until you realize entire buildings can't survive that kind of sideways shove. More than 5,000 people lost their lives. 43,000 were injured. Nearly 400,000 buildings were irreparably damaged. This disaster hit one of Japan's largest industrial zones. And when you mess with a place like that, the shock doesn't stop at the shoreline. The damage was $200 billion US in losses, from smashed buildings and infrastructure and many businesses shutting down. Kobe's port just collapsed. Only 30% of the Osaka-Kobe railway lines worked. Part of National Route 28 literally vanished into the ground. Schools, hospitals, and municipal buildings, 85% of them took damage or were unusable. Fires broke out across Kobe, almost 300 separate incidents, burning the equivalent of 70 US city blocks and taking another 600 to 700 lives. Almost 100,000 people permanently left the region, 2.5% of the whole population gone in less than a year. And here's a detail that stuck with me. So many bridges failed that engineers suddenly had to confront how poorly older designs handled lateral shaking. Houses with heavy tiled roofs, built to fight typhoons, crumbled because all that weight sat too high. But the newer homes made after the 1981 building code revision stood. And that's when Japan realized that modern seismic standards were crucial to follow. Japan threw $58 billion US into restoring the region. Power came back in days. Roads and rail returned in 5 to 8 months. The main expressway took 21 months. The port was fully rebuilt in just over 2 years. And by then, all debris was cleared. Within 15 months, manufacturing jumped back to 98% of its old level. Stores reopened. By 1999, Kobe's economy reached roughly 75 to 90% of pre-quake levels. Japan overhauled its disaster management system entirely. They set up the Central Disaster Management Council and rewrote building codes. They upgraded everything from emergency drills to fire-resistant city layouts, and they launched the Earthquake Early Warning System that now gives Japan those precious few seconds before shaking hits. The same system that saved countless lives since 2007. But despite all this improvement, the Kansai region still sits on dangerous ground. The Roku Awajishima fault system, the same one that snapped in 1995, still runs under them. The 2018 Northern Osaka quake and the 2024 Noto Peninsula quake reminded everyone that this threat didn't disappear. It just waits its turn. A future large event on that system could hit even harder simply because the region has grown more complex, more interconnected, and more economically loaded. So Kobe wasn't even a triggered double fault rupture, but it still broke a major industrial hub, reshaped a national economy, and permanently changed global shipping routes. That's why when scientists started talking about two joint faults firing off back-to-back in Cascadia and San Andreas, you don't even have to imagine the consequences. We already got a preview in 1995. The floor starts quaking like it's alive. Books, mugs, and lamps leap off shelves. Your feet slide, your body sways, and you can barely stay upright. It stops for a second, but then it shakes again and again. More than 1,000 times just in one day. This is not how you imagined your trip to Santorini, but it's the new reality. The Santorini seismic swarm started in January 2025. In less than 1 month, there were, get ready for it, more than 20,000 reported earthquakes. For comparison, most cities on Earth go through one small, barely noticeable quake in a year. It all started with small jolts that residents could feel, but tourists might have mistaken for large trucks driving nearby. But by February, things got serious. A magnitude 5.3 quake struck. It's a moderate-strength earthquake, but it was strong enough to rattle homes, break windows and dishes, and terrify the island's population. The Greek authorities declared a state of emergency for Santorini and Amorgos. Thousands of people had to leave their homes. Schools closed, and hotels temporarily evacuated their guests. Santorini is famous for its volcano, the one that blew up in a massive eruption around 1600 BCE and inspired the legend of Atlantis. It's still considered to be active, although there have been no significant eruptions since the 1950s. So it would be logical to blame this monster for all the drama. But nope, these tremors weren't volcanic. Experts said what was happening near Santorini looked like a seismic swarm. It's a series of smaller quakes all happening in the same area. They are happening along faults, which are cracks in the Earth's crust that can suddenly shift when the tension gets too high. Think of the ground like a giant, stressed-out Rubik's Cube. At some point, it twists and snaps somewhere. Near volcanic areas like Santorini, fluids moving underground can sneak into these cracks and make them easier to break. Plus, there's the natural stress from tectonic movements. It's like adding oil to a squeaky, overworked hinge. Suddenly, everything slips. Nobody knows exactly what's coming next. Tracking thousands of tremors isn't easy. Many of them are too small for traditional seismic sensors to pick up. But this time, scientists have their new best friend to help out. I'm talking about artificial intelligence. Thanks to machine learning, researchers can detect patterns in tiny vibrations that humans might miss. This technology has helped a lot to understand the swarm. It lets scientists map which parts of the crust are most active and even predict possible future activity. The AI analysis suggests the quakes aren't random. They seem to be clustered along a fault line near the underwater Colombo volcano. This area has a long history of seismic activity. Even though Colombo hasn't erupted recently, the magma beneath it might be subtly shifting the crust, and it adds tension to the tectonic plates above. It's like a simmering pot. Nothing boils over yet, but the heat is definitely building. The swarm has subsided after a couple of months of constant shaking, but it doesn't mean it's over for good. Even after a lull, another swarm could strike, or a larger quake could happen along the same fault lines. That's why scientists are now studying the data collected from the swarm. If you're thousands of miles away from Santorini and don't have plans to visit, it doesn't mean you're 100% safe from a similar scenario. Seismic swarms like the Greek one happened in the Caribbean, Iceland, and Italy. One of the best documented swarms in history happened in Japan, in a suburb northwest of Tokyo. It was all going on in a town sitting on a seismological observatory, like a secret underground lab for tracking earthquakes. The swarm kicked off in August 1965 with just 3 earthquakes that were so weak nobody could feel them. But things escalated fast, and 3 months later, 100 quakes a day were strong enough for people to feel. On one day, the observatory recorded almost 7,000 quakes. Out of those, 585 were strong enough to actually shake the ground, meaning you could feel a quake roughly every 2.5 minutes. Scientists figured out that the swarm was caused by fluids moving underground, kind of like the Earth's crust, stretching and bubbling. Studying seismic swarms helps scientists predict earthquakes better, understand how Earth's crust moves, and even prepare for future natural disasters globally. For instance, if they can link the patterns of tremors to magma movement or tectonic shifts, they can apply similar models to volcanoes and fault lines in Hawaii, Iceland, or the Pacific Northwest. Santorini is like a living lab where they combine modern tech with traditional knowledge. AI, seismographs, and satellite imaging add to centuries of human observation. The locals who have lived through quakes for generations contribute insights about small tremors, changes in groundwater, and unusual animal behavior. All this helps scientists refine their models. Santorini's swarm has surely grabbed the attention of the whole world, but it's not the only place on Earth with some intense seismic activity. But what makes Santorini unique is its combination of historical volcanoes, underwater fault lines, and the fact that it's a real tourist magnet. The island is not so large, and the effects of even moderate tremors feel stronger and more dramatic than in other regions. In other places, though, even more serious earthquakes, tsunamis, and volcanic activity are regular news, and the people have learned to live with them. Japan is one of the regions on Earth where earthquakes happen the most because it sits on the edges of 4 tectonic plates. There are around 1,500 of these earthquakes each year that are noticeable. Because of this, the people in Japan have learned to live with earthquakes. There's even a law that sets a rule that buildings in the country should be able to handle earthquakes up to a magnitude of 7 without falling apart. An update 30 years later said that buildings should only have minor damage in such earthquakes and still work as usual. But if an earthquake is even stronger, the law says the building's main job is not to collapse, but to save people's lives. At the most basic level, buildings are made stronger with thicker beams, pillars, and walls so they can handle shaking better. They even construct some buildings on thick layers of padding that separate them from the ground completely, which helps protect them during an earthquake. A skyscraper might sway back and forth a lot and move up to 5 feet, but it won't collapse. On the other side of the Pacific, scientists from the U.S. Geological Survey have studied a dangerous area along the U.S. West Coast. It's called the Cascadia Subduction Zone. Over the past 14,200 years, there have likely been at least 30 big earthquakes in this region. One major quake happened every 500 years on average. But for a long time now, Cascadia has been quiet, and the scientists are getting worried. They think this might be because the area is locked, so the tectonic plates are stuck together and building up a lot of pressure. At some point, a part of the seafloor could suddenly break and move forward by several feet. The shaking would be just 5 minutes, but it would create a powerful tsunami as the seafloor shifts that would last for 10 hours. If it happens, it's going to be the worst natural disaster in the country's history, according to experts. This could make the hillside slide and crumble and take down roads and bridges. Around 620,000 buildings could be badly damaged or even collapse. Scientists are hoping that thanks to advanced AI tech and local communities, they'll be able to better predict earthquakes like this and the one in Santorini. This could save thousands of lives. And for now, we must not forget that the Earth doesn't take vacations when it comes to seismic activity, even in places where you go on vacation. On January 26, 1700, one of the biggest earthquakes in history hit off the coast of the United States. It had a magnitude of 9, which puts it in the top 10 most powerful earthquakes ever recorded. This earthquake triggered a huge tsunami and changed the coastline all the way from southern British Columbia down to northern California forever. Back then, the area wasn't very populated, but thanks to some clever research, scientists figured out exactly what happened that day by looking at old geological records, tree rings, and even some history from Japan. On the same day as the earthquake, a massive tsunami also hit Japan's eastern coast. For a long time, no one connected the two, but in the 1980s and 90s, researchers realized the tsunami in Japan had been caused by the earthquake in the Pacific Northwest. They were also able to pinpoint the exact day, January 26, 1700. They even found old trees in coastal Washington that had all perished around the winter of 1700, which matched up perfectly with the timing of the earthquake. The earthquake came from the Cascadia subduction zone, a fault where the Juan de Fuca plate slides under the North American plate. This fault stretches about 700 miles, from northern Vancouver Island in British Columbia to Cape Mendocino in California. The pressure from the moving plates builds up over time, and eventually, another big, devastating earthquake will hit the same region. It's just a matter of time. By looking at the geological records, past tsunami deposits, and signs of land level changes, scientists can figure out how often these huge earthquakes happen. Emergency planners have been preparing for the next big quake, often calling it the big one. Scientists believe earthquakes in the Cascadia subduction zone happen every 200 to 1,000 years, and since the last major one was over 300 years ago, the Pacific Northwest is definitely due for another. When it happens, the earthquake is expected to be as big as the one from 1700, but this time, it'll affect around 15 million people. The devastation will be severe. Buildings will collapse, roads and runways will crack, and bridges will fall. Communication in and out of the area will be cut off. But the worst part? The earthquake will trigger a massive tsunami that might hit parts of the Washington coast in as little as 10 minutes. It's not a matter of if, but when the Cascadia subduction zone will break. When it happens, it will be the worst disaster the US has ever faced. Worse than the Hurricane Katrina or Superstorm Sandy. It'll impact an enormous area, stretching from southern British Columbia all the way down through Oregon to northern California. That means millions and millions of people will be affected. Fairchild is considered a backup staging area for handling the aftermath of the earthquake, with Grant County International Airport in Moses Lake being the main one. For those who will survive the initial quake and tsunami, the aftermath could be just as disastrous. Aftershocks will follow, and transportation will be a mess. Roads will be damaged or completely blocked, airports will shut down, and most of the main routes, like Interstate 5, will have bridges destroyed. This means food and water supplies will be cut off, and it will be incredibly difficult for help to get in or for people to escape. Gas pipelines will most likely be damaged too, and restoring them could take anywhere from a few days inland to weeks or even months along the coast. Power outages will be widespread within 100 miles of the coast throughout the entire Pacific Northwest. And water could be out for 3 to 7 months. Even telecommunications will be down for 2 to 3 months across the Pacific Northwest, Alaska, and even parts of East Asia. The good news for eastern Washington is that it will mostly avoid the worst of it, thanks to natural barriers between the west and east sides of the state. The tsunami may hit the Columbia River Gorge, but it will lose energy quickly because of a sandbar under the river. The Cascade Mountains will absorb much of the earthquake's impact, so the east side won't feel it as strongly. And since eastern Washington won't get hit as hard, it'll be up to them to handle the aftermath of the quake. That means helping western Washington, taking in refugees from the areas that got destroyed, and delivering supplies to where they're needed. Scientists have looked at other major 8.0 to 9.0 magnitude earthquakes like the ones in Chile in 1960, Alaska in 1964, and Sumatra in 2004, and Japan in 2011. These kinds of quakes can shake the ground for anywhere between 6 to 10 minutes, and that's a long time for the ground to be shaking. Such quakes are super intense because they happen close to Earth's surface, so it's not just a quick shake. It's a long, strong one that can cause a lot of damage. If the Cascadia earthquake and tsunami were to hit tomorrow, over 13,800 people could lose their lives, and about 107,000 people could be injured. The economic toll in Washington, Oregon, and California could top 70 billion. To put that into perspective, we can compare these numbers with some other major earthquakes. In Chile's 1960 earthquake, about 1,650 people lost their lives. The 1964 Alaska quake resulted in around 140 lives lost. The 2004 Sumatra earthquake and tsunami took the lives of an estimated 280,000 people. And the 2011 Japan earthquake and tsunami caused over 20,000 casualties. Authorities know about the dangers of the Cascadia fault, but even with all the planning, no one can say for sure what will be needed when the big quake hits. Right after the earthquake and tsunami, the areas outside the immediate disaster zone won't be able to help much because roads and airports will be destroyed, and resources will be limited. How can we deal with this kind of disaster and its effects? We don't have all the answers yet. Right now, let's focus on the Cascadia subduction zone. It's a huge fault line that stretches about 620 miles from Vancouver Island to Cape Mendocino in California, sitting about 93 miles off the coast. It's like one tectonic plate is slowly sliding under another. When the plates are close to the surface, about 18 miles deep or less, they get stuck because of friction, kind of like pushing two rocks together. Over time, this creates a lot of pressure. When the pressure finally becomes too much, the plates slip, causing a massive earthquake. This is called a megathrust earthquake, and it can be huge. Below the area where the plates are stuck, there's a zone where the plates move really slowly. We're talking about just a few inches every few months. This slow movement helps to release some of the pressure, but it also builds up more pressure on the parts of the fault that are still stuck. This means that over time, it increases the chances of a huge earthquake happening. These massive quakes, called Great Subduction Zone earthquakes, can be stronger than magnitude 8.5. Megathrust earthquakes are the biggest earthquakes that happen. They can go over a magnitude of 9.0, which is insanely powerful. Just to put it in perspective, a magnitude 9.0 earthquake releases 1,000 times more energy than a 7.0 and 1,000,000 times more energy than a 5.0. These earthquakes happen when a lot of pressure builds up in a part of the fault that's locked, which means the plate can't move past each other. When that pressure gets too high, the fault finally ruptures, releasing all that built-up energy in one massive shake. The Cascadia subduction zone is super long. That's why if it were to rupture all at once, it could produce a large earthquake. Scientists have studied this region and found that about 18 miles below the surface, the fault is completely locked. The plates there aren't sliding past each other. But deeper down, the plates start to slide more smoothly, causing less friction. This is important because it tells us how much stress is building up in that locked zone, and how it could eventually lead to a major earthquake.